Okay, now let's briefly discuss the issues related with the ceramic materials. And for that type of materials, we prefer to have use direct sintering. And what we do, we maintain the high temperature in the bed, in the machine, and then use laser to accelerate the sintering operation. But obviously, we will have highly porous, let's say, products, and that's why we need to do some post-processing, as in the case of some special metal sintering processes we need to do, put these parts into the oven and try to obtain higher densities. We can also have some chemical in the sintering operations, which is not valid for metals or polymers, but we can do it for the ceramic materials. And we may also have an indirect processing, and in this time, after you define all these powders, then you may have the brown part ready, which sometimes we call it as green part, and you can do infiltration as in the case of metals. It's very similar to that, and our main aim is again to decrease this porosity levels. Now you are wondering how this infiltration works. I will show you a video. Yes, this is working, I think. Let me share it with you. Yes. This is again the same company. This time they are producing metal parts. Again, their design, CAM software. I think this is directly on the printer. After they set up their build volume, they put their box into the machine. It's the bending, it's not the bending obviously, but sintering, or we can say powder bed. Let me show you once again. Yes, this is a powder bed, and they have such a flexible system since once they are doing operations in another powder bed, they want to continue with printing operation. So pushed into the center. Now they are printing various, as you see, metals: stainless steel, bronze, tungsten. This is a special process. We will talk about it actually in the next chapter, but you don't need to know the details. That's a bit different. I just want to show you the infiltration process. Sorry. Now the part is finished. They have a kind of a cleaning unit for their heads. Now fabrication is over. They are removing the bed, and we'll do some extra operations. This is sintering operation. They put the box actually into the oven to remove all these binders. Now they will remove the powders around the part. And another vacuum system removing the powders around. Now we know that this has high porosity levels. And now, in order to increase its density, they will do an infiltration operation. And we will see how it works in a moment. Yes, this is the preparation steps for the infiltration. They kind of put them into a box, and these are some ways for copper actually moving to the porous regions of the original products. So you may assume that there is kind of channels where our liquids will flow and go into these porous regions of the product. This is the infiltration material, probably copper. They're also pouring it around. I think this are not copper, but this is for, I think, heat insulation. Now they put it this new box, form box, into the furnace, and infiltration will start. Since they cannot actually record the interior, that's why they show these fundamentals with an animation. Now that's how actually infiltration works. So we have copper here. Now it will be melted. And it will flow into the product and fill all these gaps, all these porous regions inside the products, and we will have about 99% of density. Now they are going to remove it. Yes, the product is ready. They obviously cut it from the runners, like in the case of casting process. And I think they do also little finishing, but it's not that important. Yes, that's it. Any questions, guys, about this infiltration process? Okay. So how can we have different variations of powder bed fusion systems? We might have some differences in terms of powder delivery method, how we are spreading the powder, whether we are using kind of cartridges underneath, or we may be using hoppers upside of our table. We may have different heating processes. You may use resistances or kind of lasers, IR heaters. It's up to you. And the type of energy input might be different. You may use laser or electron beams, and there might be differences in terms of atmospheric conditions. For the polymers, you don't need to have some special ones, but if you are fusing metal powders together, then it's better you have a kind of an inert atmosphere, or you pump some inert gases into the environment, or have a vacuum atmosphere. So we will have no gases around, and we cannot have any sparks or fires generated. And lastly, there might be some difference in terms of optics they are using. So by having these variations, you may come up with various powder bed fusion processes. If you, for instance, make use of lasers for low temperature processing, and they are mostly designed for polymers. Since in the polymers, the melting point temperature is not high, you can make use of low powered lasers, and do your sintering or fusion process. But for the metals and ceramics, it will not be the final, let's say, process. It will be a kind of indirect processing, since your laser power will not be able to melt the metal powders. So that's why you need to do further sintering and infiltration process. And that's why we call it as an indirect processing of metals. And we know that there are lots of printers using low power lasers for the manufacturing of polymers. One of them is, as you know, Sintering 2000. And an example I showed you, EOS. EOS has many types of printers using SLS technology for the polymers. But for metals, if you prefer to melt them, if you want to complete this fabrication process right on the machine, then it's better you use a high power laser or an electron beam and melt these powders, and they will be joined. At the end, you will obtain the final product. Oops, guys, I'm sorry. Okay, and now we have, with the help of these improvements in terms of different technologies like laser, optics, some handling system, powders, since there are companies working on the sphericity of the powders and they want to obtain pure spheres all the time. And with the help of them, we can increase. These days, the new models have better accuracies, better temperature uniformity, since what they do is that they sometimes put some thermal cameras inside the machine and try to check if the temperature is uniform inside the machine or not. Even they sometimes monitor the table and try to see if they need to update the scanning pad of the laser or not. So we have such improvements in these technologies. Another issue with the help of optics and with the help of improvements in the laser technology, the fabrication speeds are improved, and we have better repeatabilities, and the surface qualities are improved with the help of these advancements in the technologies and materials. This is an example system, very similar to the one actually I introduced you. This is from, I think, 3D Systems. The company is called 3D Systems, and it's their Center Station System Pro SLS system. And this is the main printer. Here, the part is fabricated actually. We have a chiller. I didn't show you while introducing you the EOS, but they also have a chiller. Chiller is kind of a cooling unit for the laser. We have a water flowing inside, and it's trying to keep the temperature of the laser at usually around 20 or 21 degrees. And sometimes, as we discussed, we may have inert gases inside this chamber, and they have actually these 3D systems make use of such a nitrogen generator. And then, as you see inside this room, they have a large room for this printing operation. On this side, they have recycled powder system. They kind of do take this powder out of it and try to recycle it by their they do a kind of a mixing operation so that at the end of it, they will have a uniform mixture. Another thing we have seen also on X1 system, this is rapid change module, so you don't need to wait for cleaning or recycling operations. If you have an extra, let's say bat, we can simply push it inside and start another printing process. Any questions, guys? And as I discussed in the previous slide, they usually have modular designs. And in order to have a continuous fabrication process, they have multiple build platforms. Once it's done, they remove it and then put another new platform so that the fabrication can continue. And another property is that they might have multiple build platform sizes. In the previous lecture, one of your friends pointed out why don't we use smaller ones? Some companies they have smaller ones, but not all the time. They just have one or two options. They cannot actually adjust the size of the platform according to the parts to be produced. It's quite difficult. Then we have usually automated recycling systems, as we have seen in the previous one, the 3D systems printer. Another issue is about automatic feeding of powder. So these are the new improvements in powder bed fusion systems. And I mentioned about this one, the thermal control. They make use of some thermal camera and also some thermocouples around the machine, and they try to keep this temperature at the desired values. And this is done with the help of a closed-loop control approach. They are controlling the temperature in a closed-loop manner. This is a very simple schematic. This was from our textbook. It's showing the fundamentals of EOSint, the one actually I introduced you. Not complicated. Obviously, we are scanning the layer and then lowering the platform, recoating it with the new powder, and then doing this sintering operation once again. So this is the main loop and the EOSint machines. And for the metals and ceramics, as we discussed, sintering itself is not enough, since the powders will not be joined together firmly. We always have porosities in between. So that's why if you want to have a single machine to join metal powders or ceramic powders together, you need to do melting operation. And we name this process as selective laser melting. Instead of sintering, we use selective laser melting. And we know that these powders are difficult to process. We need to use high power lasers, but sometimes even that lasers may not be enough. So people start to use electron beam to melt these powders in a very short amount of time and join them together. Another issue is that we need to have rigid base platforms, base parts actually. I'm sorry, this was off, so let me turn it on. Yep. So they start with a kind of a substrate, some metal substrate, a very little thin one, and then they build their product on top of this one. So after the part is finished, they need to do cutting operation. They may use wire EDM, electrodischarge machining. So they should find a way to remove this part out of the substrate. This is a fundamental issue in selective laser melting. You cannot directly print your product on the bed. Otherwise, you will harm your bed and you will not be able to use it for the next time. This is an example system, and here they are using two different types of material at the same time. They have two different chambers. By using their, let's say, special mechanism, they feed two materials at the same time, or one material for a specific layer and another material for the upcoming layer. So people are trying to find such better ways for high quality products. Any questions, guys, about these issues related with metals and ceramics? No questions? Okay. And then now let's have a look at electron beam immersion. And I said that some metals are quite difficult to melt, and in such cases, we prefer to use electron beam instead of laser beam. And we call this process as electron beam melting. And in the schematic, you can easily see that we have electron beam generated, and we have tungsten filaments, or I don't remember exactly, but they need to use obviously some filaments to generate these electrons. And then this part is anodes, obviously, and we have some special coils for focusing the beam. And then this part is important. They have such special coils which are actually used to control this XY motion. Again, as in the case of galvanometers or lasers, we are not moving the laser on the bed. The electron beam gun is actually stationary, but with the help of these deflection coils, they reflect this electron beam anywhere on this bed. And they need to do some, obviously, increase current, decrease it, and try to shift this laser beam on the bed. Another important issue about this electron beam melting is that we need to have vacuum chambers. We shouldn't have any gases inside. Otherwise, we'll have sparks. We may have some fire. So this is a must and important issue for electron beam melting, and also it's quite costly and very difficult. You need to have special pumps. These pumps will move the air inside and try to keep the pressure very close to 0 atmosphere. And as I said, this is highly difficult. But other fundamentals are very similar. Again, we need to move our platform downwards, and we need to again have some powder feeding systems. Here they are using hopper and a kind of a blade here. It's moving to left in this case, but you may also use various approaches. But the important thing is that you should have a vacuum environment, otherwise you will not be able to do the process. And this was mostly developed by the company called Archem. It's I think a Sweden company, and later I think General Electric acquired them. They are now operating underneath GE. Any questions, guys, about this electron beam melting process? It's again an powder bed fusion process. So there is nothing different. This is powder bed fusion process. And we are melting it. Instead of sintering, we are doing a melting operation.
Hocam ben şeyi soracağım. Sintering'de mesela metalleri
Now
kullandığımız...
let's compare
Hocam sesim geliyor.
electron beam melting with selective laser melting. The main difference is obviously is that in SLM we are using laser, and in the electron beam melting we are using electron beam. Can you hear me, guys? I think some of you have problems. But...
Hocam sesim geliyor mu? Ben bir soru soracaktım da.
Yep.
Ya şeyi soracağım ben. Metallerde sintering olayını kullandığımızda kesinlikle post processing yapmak zorunda mıyız? Melting yaptığımızda kullanmıyoruz post processing, ama sintering, yani metallerin sintering olayında kesinlikle kullanacağız değil mi post processleri?
Yep. It's like powder metallurgy. If you do not have any, let's say, further processes, then you can easily break your part into parts, into smaller parts. They are in green state. You can call them as green compact, sometimes brown part. They do not have enough strength, so you cannot use them after they are sintered. You need to do further sintering operations.
Sağ olun hocam.
You're welcome. Any other questions, guys? Okay, we said that as a thermal source, obviously, EBM systems are using electron beams, and the SLM systems are using for the atmosphere, not to have any air inside. In order to keep that pressure equal to 0, we need to have a vacuum environment. But for the SLM, we may use some inert gases like nitrogen or helium, but mostly they prefer to use nitrogen. And for scanning, regarding the lasers, we may use galvanometers, such mirrors, but on the beam side, on the electron beam side, we need to use some coils. And another thing, for the energy absorption of the parts or the powders, it's related with the conductivity of the powders. So if you cannot use non-conductive materials in electron beam melting, you can only work with conductive materials. But for the selective laser melting side, the energy can be absorbed depending on the absorptivity of the materials. And these might be polymers, metals, and ceramic. You don't have any limitation. It just depends on how much these materials are absorbing energy. But for the EBM side, we can only make use of conductive metals. Another thing, for the preheating, we discussed that it's better we do some preheating, since otherwise you need to use high power systems. And for the selective laser part, selective laser melting part, we prefer to use IR heaters, infrared heaters. But for the electron beam side, we directly use the beam itself. We don't have special heaters around, since we want to have a proper controlled environment. That's why we only use the electron beam itself. And other issue about properties are like scanning speed. For the electron beam, it's quite fast, since it's easier to deflect the coils. and they are magnetically driven. By increasing their current a little bit, you can easily position your electron beam on the table. And if you consider the selective laser melting, we are using obviously lasers, and it's limited by the inertia of your galvanometer. But again, not that high. They are they quite have high speeds compared to, let's say, FDM process. And the energy costs are a bit higher for the laser side, but for the electron beam, it's not that much. And surface qualities on the electron beam side is quite poor compared to the laser melting side, since we are actually increasing temperature to very high values, and once they are actually cooled down, we will have such bumps on the layers, and that's why our surface quality, surface finish is a bit poor compared to the laser side. And since this is somehow related to each other, these two properties, the surface finish and feature resolution, we cannot have very small features fabricated on the EBM side, but this is not as a big problem in the laser melting systems. This is actually the surface qualities and feature size are very good for polymers, but we also have some problems for the metals. And their energy costs are a bit higher. Their surface finishes are not as good as it is in the polymer materials. So these are the main things we can say about electron beam melting and selective laser melting. Any questions, guys, regarding these operations for metal powders? So you can see the typical microstructures in the SLM systems and EBM systems. This one is EBM, and this one is SLM. As you see, they are completely different. We have a rapid solidification here on the EBM side. That's why we have such longer grains. But on the SLM part, we have much circular grains, and it's quite clear to see this, let's say, scanning patterns. And as far as I know, this should be top view. You can check it from your textbook, but this is the top view. Now we will focus on a bit different issue. In the previous ones, we were always using a kind of a point-wise process, right? We have a laser or a electron beam, and it's just scanning the whole plate, whole powder bed, right? But now instead of that, we may have different solutions. The first one, for instance, might be a line-wise case, and the other one is layer-wise case, which might be similar to DLP process, but we'll now have a look at them. Not exactly the same, at least the fundamental idea is the same. Now let's have a look at the first one. This is called as mask-based sintering. So what do we have here? We have a mask, special mask, and then we have some IR heater here, and inside these openings we will have heat actually transferred, and with the help of it, the temperature of this region will be improved, increased, and we will have these powders sintered together. But the thing is that you need to have such mask for all the layers. If it's an 2.5D shape, then with a single mask you can do it. But if it's a complicated shape, then obviously it's not quite doable. You may need to use different approaches. Another issue is that you cannot have such much gap between this powder bed and the level you are holding the mask. It should be as close as possible. Otherwise, this heat obviously will be distributed, and we may also sinter the powders around. So that's why you should keep this gap as small as possible. Now let's have a look at the second one. is printing on absorptive enhancing agent. So we are printing absorptive enhancing agent in the part region. So this is the inkjet. This is a kind of a head. It's moving and is spreading some absorptive enhancing agent. With the help of it, what happens? Since we are heating, with the help of this IR heating, the regions which have such special agents will be sintered. The other regions will not be sintered since they don't have such an agent inside. So this is a kind of an maybe a line-wise approach. With your inkjet, you may move from left to right and spread this special agent, and with the help of this heater, this cross section will be sintered and the rest will not be sintered. Let's have a look at the last option. This is printing of a sintering inhibitor outside the part region. So this is important. Right now, we are spreading a special, let's say this time, chemical inhibitor to the outside of the part. Which means that once we spread the special agents outside, even though you increase the temperature of your bed, these parts will not be sintered together. Since it's an inhibitor, it will eliminate the fusion process. As you see, we have such different applications, but we don't have much of these in the commercial products. In the commercial ones, they mainly use a laser, and the laser simply scans the bed and tries to sinter the powders or melt the powders together. Any questions, guys, on these 3 different cases? They are with different, as I said. And we can say that this is an example of a layer-wise approach, similar to DLP, but the difficulty is that you need to have hard cover or hardware for all your masks. And if you have a 2.5D shape, then with a single one, you can do it. But for complicated shapes, having lattices, having formed surfaces, it's not doable. Any questions regarding the slides? Okay. So in the process, we have many things, right? We have heaters, we have lasers, we have platform going up, we have cartridges. Platform going down, cartridges going up. We have blades moving right to left, left to right. We have layer thicknesses. We have the size of powder. So there are many parameters, and some of these parameters are related with the laser or the electron beam you have. Some of them are related with the scanning, whether you have, let's say, two shells or just a single one, or whether you are using a zigzag pattern. So they are related with the scanning. And we have powder related parameters, their quality, their size, their uniformity. And we have temperature related issues like the melting point temperature of the powder, temperature of the environment. And so the thing is that they are quite interdependent. So we cannot easily have a single equation between one of them and another one. They are highly interdependent. They affect each other. That's why it's written as here that mutually interacting. So there are lots of research going on this modeling part. They are trying to relate all these parameters together, but we don't have a complete, let's say, model. Some computer engineering software are also trying to come up with such models. They are all still continuing on the development of the software, but not finalized yet. So we have a nice discussion in our textbook. Please make sure that you read there. There's a nice discussion on how these parameters are affecting each other, especially in the powder bed fusion systems. For instance, let's have a look at some scanning patterns. This is a strategy employed in powder bed fusion systems. We have 2 contours, as you see, and then such a grid. And inside these grids, we may have such further patterns. As you see, they are not always in the same direction, they change inside these smaller grids, sometimes vertical, sometimes horizontal, or sometimes diagonal. So there are many papers on these issues, and they try to come up with the best actually scanning pattern. And we have a simple relationship, a very simple one, as you see, in terms of applied energy density and power, scan velocity, and scan spacing. And we can say that simply, if you increase laser power, then obviously our applied energy, the density of this applied energy will be improved. But on the other hand, if you do it in a faster way, then you will be decreasing the amount of this energy, applied energy. And lastly, if you increase the scanning spacing, for instance, let's compare these two. And once you increase the spacing, then our EA, the applied energy density, will be decreased. So we can simply say that there is such a relationship between these four parameters or four variables. And we have some typical values. For instance, in SLS, selective laser sintering system, the scan spacing is usually around 100 micrometers. And if you have an, let's say this is the scan spacing, if this is 100 micrometer. But if you are using a laser beam within, let's say, spot size of 300, let's say micrometer, then obviously while this one is moving, if this is the center of the laser, while it's moving, you have obviously multiple passes from all the points. And so you should be careful about it. You should know all these parameters and try not to melt maybe the previous layers or the regions where you have already done the fusion operation. And we discuss these issues, and we know that after the melting, we need to have solidification, and it's quite difficult for the metal powders, and they always, the size of the, let's say, grains, their elongation directly affect the quality of the part, whether you have elongated microstructures or circular ones, they highly affect the quality of the parts you want to print. And considering the quality of polymer systems, polymer-based parts, we have similar properties with injection molding parts. But the thing is that we have less elongation. Their elongation is not much. They are quite brittle, but their strength is somehow similar to the injection molded products. And these days, we also have some thermoplastic polymers, and they have flexibility. So if you want to have higher elongation, then you may need to use different types of polymers.